Okay, so today I would like to start with discussing Narayan compactification. And this is actually a very interesting class of model, and it captures several important features of conformal field theory and its use in string theory. I think this is pronounced as Narayan. Sometimes the more typical spelling is Narayan, but somehow he uses this spelling. Oh, I forgot to bring my chalk eraser. Okay, so next time I'll bring my chalk eraser. Okay, so we start with toroidal compactification, and so we consider a d-dimensional torus. Okay, and so we have already discussed the basis of the metric. So I started with some metric on the torus, but then I changed the basis of the torus so that we can write this as EIA, EJA summed over A, and so this would be a plane. Okay, so and then there, so this gives you, instead of expressing torus as a sort of square torus with arbitrary metric, we can express this torus as a d-dimensional Euclidean space divided by the lattice, where the lattice is generated by integer multiple of so these are the basis of the torus. And so with respect to this expression of the torus, string worship coordinate x have an expansion in terms of p left and p right, and it has a momentum, center of mass momentum, and winding number, which takes value in the lattice and the dual lattice, and which can be expressed as well, it's the other way. Okay, so the winding number takes value in the dual lattice, in the lattice, because so what winding number does is to go around this torus. So if you have, so this is a sort of caricature of torus. This is the case when d equals 2. So the string can wind around the torus this way or this way, and it counts how many times it winds around. So it's natural that the winding number takes value on the lattice. And the momentum is conjugate to that, so it takes value in the dual lattice. Okay, and it's useful to introduce a basis. It's useful to combine this lattice and dual lattice to make 2D-dimensional lattice. Okay. So this 2D-dimensional lattice is generated by this type of thing and this type of things. Okay, so you have this linear combination. There is actually a nicer basis of this, which is 1/2 of EJA minus EJA, and E star I, which is E star AI, E star AI, which if we use this notation, then we can write the momentum which is in this, the combination of this momentum to be a linear combination of E hat star I and I plus E I hat Mi. Okay? So you can write the lattice in this way. So this is 2D dimensional lattice. So it's a combination of the lattice and the dual lattice. And this lattice has various interesting structure. So as you can see by the definition, there is a natural metric that we can introduce in this space, because suppose you have two of them, and suppose you take in a product of them, then we can actually define a metric on this lattice by, in this basis, this metric, the d dimensional lattice. So one d dimensional metric with positive signature and d dimensional space with negative signature. And by this definition, E hat Ej is 0 and its dual directions is 0, etc. And then this direction is connected. Okay, and so if you define it that way, then for example, if you have two momenta, its inner product is given by this. And so therefore, in particular, it takes value in integers. And so let's call this lattice as the lambda hat. So lambda hat, as I said, is defined to be the linear combination of Ni E hat I plus Mi E hat star. Okay, so this is a lattice, and in this lattice, lattice has this structure. But another important property of this lattice is that it's self-dual. That is that if you consider dual of this lattice, so the dual of the lattice means that it's a collection of all the vectors whose inner product with the lattice is an integer and invertible. And it turns out that the dual of this lattice is the same as the original lattice. So what this suggests, what this shows is that that if you have a string on TD, then the momentum and the winding number makes a even self-dual lattice. Oh, by the way, so I forgot to say that because of this, if you consider inner product of momentum by itself, since these two terms are the same, this in particular is an even integer. So this is called even self-dual lattice. Okay, so this is actually a very important concept in the forum. So for example, when we discuss heterotic string construction, this becomes very important. And so I hope it's okay. I hope you can see that. So it is actually easy to see that if the lattice is even and self-dual, then the modular invariance is guaranteed. In fact, when you define, for any lattice, suppose this is a lattice, then we can define the partition function. So suppose this is 2D dimensional lattice. Then with respect to this, we can define this partition function. With respect to this given lattice, we can define this partition function, and we can show that this partition function is modular invariant. Z tau hat is modular invariant if and only if this lattice is even and self-dual. Okay? So let us see how it works. Okay? So modular invariance, as we discussed earlier, is the invariance of this. So we write Q is equal to e to the 2 pi I tau. And the modular invariance is the invariance under tau goes to A tau plus B, C tau plus D, where A, B, C, D is in SL to Z. Okay? So this is the invariance under this transformation. And this is necessary for the two-dimensional conformal theory on genus 1 Riemann surface is well defined, that it only depends on the conformal surface. And but important thing is that this is generated by tau goes to minus 1 over tau, and tau goes to tau plus 1. So in order to check the modular invariance, we just need to check the invariance under these two conditions. So the easy things to check is invariance under tau goes to tau plus 1. So let's first check this. So this Dedekind delta function part is automatically invariant. So this is eta is equal to q of 1 to the 24th and the product. And then this product part manifestly is invariant because q is invariant and the tau goes to tau plus 1. And then this is fractional power, but we have absolute value square, so therefore this is invariant. Okay, so that's not the program. And but we need to check this one. So if you do this, then q to the 1/2 of p left square q bar, to the 1/2 of p right square goes to the same thing. But you also have pi I of p left square minus p right square. Because if you do this, q goes to e to the 2 pi I times q by definition. And since we have half of p left square, so it gives you pi I of p left square minus p right square. So if lambda hat is even, then the definition of this is that p left square minus p right square is an even integer. And so if this is an even integer, this is equal to 1. So we can check that this is modular invariant. It's more interesting to check the modular invariance and the tau goes to minus 1 over tau. Okay? So Denneken theta function, you can just look it up in table of functions or Mathematica to see that this is minus I tau of eta tau. So therefore, the prefactor 1 over absolute value of eta to the 2d give rise to some power of tau and tau 1. Okay? So the question is that how does the modular invariance works for the other part, which is this one. So this is more interesting calculation. Okay, so what we need to do is so you have this. Originally you have this, but then you change it to q tilde, which is e to the minus tau of 2 pi I. And then somehow you need to do this lattice summation to bring this back to the original. Okay, so how do we do that? So there is actually a way of, there is actually a nice formula. So to do that, I need to introduce one formula, which is a Poisson resummation. Okay, so Poisson resummation is the following trick, and this is actually a very useful trick. So suppose f is a function in n dimensions. So n is going to be 2D eventually. So this is a function defined on Rn. So this is a function on Rn. Then we can define Fourier transform of this function by saying that f of x is an integral of momentum e to the I k x sub of k. Right. So this is sort of definition of the Fourier transform. Okay. Now, so Poisson resummation is the following formula. So if you have the function and its Fourier transform, then there is a relation between the sum of a lattice and the dual lattice, which is the following things. So suppose you want to sum, not integrate this function, but sum this function over some lattice point. Okay? Suppose you want to sum this function over some lattice point. Well, we can substitute this into here. And here we need to justify the exchange of integral and summation, but so assuming this is done, as usual in many physics programs, we can write this as summation n 2 pi n summation m over lattice e to the I k m f star of k. Okay, so how do you do this summation? How do you do this summation? Okay, so it turns out, and this is something we can prove, is that the sum of m over lambda of e to the I k m is equal to 2 pi to the n of sum over n over dual lattice of delta function. So n-dimensional delta function of k minus n. Namely, that if you sum if you sum e to the ikx, where x takes value on the lattice point, then the result of summation is sum of a delta function in dual lattice. Okay? So this is actually a formula that you probably see in Fourier transform very often. So for example, if you have a circle periodicity, so suppose you have a circle periodicity 2 pi. Okay, and so you can think of this as a lattice, for example. So you have a real axis, and the lattice is an integer multiple of 2 pi. So then you have a Fourier transform like this. Okay. So now if you sum this over integer, and then the 2 pi n, so you can think of this as a lattice point, right? So then this is actually equal to 2 pi times delta, summation of delta of k minus n. The reason is that if k is not an integer, then this would oscillate as you sum over n, and then basically it becomes 0 because phase cancels with each other. But if k happens to be an integer, then for all n, this summation is 1. So you're summing 1 from minus infinity to plus infinity, and this gives you infinity, right? So that means that when k is an integer, this is infinity, and when k is not an integer, then it gives you 0. So you can guess that this should be proportional to sum over delta function where k takes value in the integer value. And then you just need to check the normalization. That if you integrate this in the neighborhood of any integer, if you integrate k in the neighborhood of any integer, and you will get 2 pi. And so this is the result. Okay? So that's sort of the argument. Is that clear? And okay. So this is generalization of this. So this is the same thing, namely that if k is not at the dual lattice point, so that means that k times m is not always an integer. In general, k times m is integer only when k is in the dual lattice point. So therefore, this is not an integer. And you're summing over all of these, and so phase cancels, and it becomes 0. If k is at the dual lattice point, then this is an integer. I think there must be 2 pi missing somewhere. So it's I guess a multiple of 2 pi. And so I need to provide 2 pi. Oh yeah, excuse me. So I think the 2 pi should not be here. 2 pi should be. I'm sorry. The 2 pi should have been here. So if k is a multiple of 2 pi times integer, then this is a 2 pi integer, and so this is 1, so this gives you infinity. So therefore you can see that this should be given by this. So we substitute this into here, and then do the integral, and then voila, we see that this is actually equal to sum over n over this is now k is now replaced by 2 pi n. So oh yeah. So I forgot some important factor, which is so this is multiplied by the volume of the dual lattice because when you integrate when you consider proper normalization, we get this extra factor. So you get volume of lambda star times summation over dual lattice of f star of 2 pi n. Okay. So you get this formula. So if you have this is a formula that works for any function. So for any smooth function, on the d-dimensional Euclidean space, if you sum over lattice point, any lattice point, then it's proportional to the sum of its Fourier transform over the dual lattice. So that's a statement. Okay, so why this is relevant to the program we are facing? The reason that this is relevant for us, maybe I should go to the next blackboard. The reason that this is relevant for our program, maybe I should make the blackboard a little bit more legible. Okay, so the reason for this to be relevant for this program is that we are considering this particular function. We are considering, so this, we apply this formula, apply this. This Poisson resummation to this particular function, which is q to the 1/2 of p left square, q bar to the 1/2 of p right square. You see the p left, p right is a point on the lattice. That's what we defined, right? So we define p left and p right to take value in this big lattice. And so you can think of f as a function on this 2D dimensional lattice. And the nice thing about this is that its Fourier transform is of the same form, except that tau becomes -1 over tau. And that's sort of the consequence of the Gaussian integral. I do not like this blackboard eraser. I do not know. I need to bring a new one. So f of p left, p right is defined to be q, namely that e to the 2 pi I of p left square minus 2 pi I tau bar, 2 pi I tau bar of p right square. So this is f. So what is f star? So kl, kr is equal to, I think there is a factor of 2 pi somewhere, but you write it as x to the n of e to the 2 pi I xl, so maybe p left square 2 pi I tau bar p right square, and now this integral is Rn, and e to the I minus I k left p left plus I of k right p right. Okay, so this is the integral. I have this sign because of the metric we used on the Narayan lattice. Okay, now we're gonna do this integral, but this integral is easy because this is Gaussian. The Gaussian, right? So we just do this integral, and so then this becomes modulo some factor of tau and tau bar. So I need to include that. So this there is a factor of square root. So this is 1 over square root of tau bar coming from this Gaussian integral, maybe 2 pi I. I should include 2 pi I. But then there is a pi I, so maybe modulo factor of pi. This is then there are n of them, so we have n. And then this is equal to e to the minus 2 pi tau of I of k left square plus 2 pi tau bar I of k right square. I think this is correct. And so this corresponds to the transformation. And then this 2 pi gets cancelled because there is an extra factor of 2 pi. So this means that the sum over p left, p right in this lattice of q of 2 pi I tau p left square minus there is a factor 1/2 I missed, probably. Q bar 1/2 p right square is equal to, so you get some factor of square root of tau bar. So this is, you can write it as tau, the absolute value of tau to the d. I think this, you can write it in this way, yes. On the summation of k left, k right in the dual lattice of q tilde of 1/2 of k left square, q tilde bar of 1/2 of k right square, and then multiplied by volume of lambda square, lambda star. Okay, so you get a factor like that. Okay, so interesting thing is that first of all, this factor cancelled with this imaginary square root of tau factor for the eta function transformation. And indeed, we get the sum of a lattice converted into sum of the dual lattice with modular transformation. Okay, so let me summarize. So what this shows. So what we have shown is that if you define the partition function for the torus, say if you shift tau to tau plus 1, then this is equal to z of tau, where which follows from the fact that p left, p right makes even lattice. On the other hand, if you have this with tau, minus 1 over tau, if you have this with tau, then this is equal to theta, and this is equal to the volume of the unit lattice in the dual lattice times the dual lattice times minus 1 over. Okay? So far I have not used anything. So this is true for any lattice. This is true. This formula is true for any lattice. However, if p left and p right is in self-dual, so if lambda is self-dual, then lambda hat is lambda hat star. So these two are the same thing. And moreover, if this is a case, well, the volume so in general, the volume of dual lattice should be inverse of the volume of the lattice, because dual lattice is defined in such a way that the inner product of point here and the point here, point in this lattice and point in this lattice is normalized to be 1. So therefore, if the size of the volume here is large, the size of the volume here should become small, so that this product is 1. So therefore, if it is self-dual, it follows that the volume is equal to 1. So therefore, it follows that lambda being even self-dual is equivalent to say that this is modular invariant. Okay. So the next question one might ask is that is the modular invariant lattice always in the form that comes from the metric. So let's investigate that. So first thing to note is that the space. Okay, so let's see what we can say. We start out by saying that space of even self-dual lattice is SO. So I think this is SO or O of DD divided by O of D times O of D divided by O of D Z. Okay. So the space of d-dimensional lattice, even self-dual lattice, is given by this coset space. Okay. So this is something that so one can derive from this condition. So for any point in this space correspond to dual lattice, lattice which is even and self-dual. So even self-dual, as I said, consists of the point which P right at is integer and point where P left square minus P right square is an integer and self-dual. Okay, and the way to see that is that if you have such self-dual lattice, then you can perform this SODD rotation and obtain another self-dual lattice. So you act this DD rotation on the set. So if you have self-dual lattice, then you have D times D, D dimensional, 2D dimensional lattice vectors. And you can perform SODD rotation. This preserves the metric. So therefore, it preserves this even self-dual property. But acting this rotation only change the basis of d-dimensional space of momentum and winding number. So this does not create a new types of lattice, so we need to divide this by this space. Now this is analog of modular transformation done in target space. And the modular transformation also maps the lattice into the same type of lattice. So this is also the same thing. So therefore you can see that this is a space of even self-dual lattice. This type of space appears very frequently in the study of string compactifications, and this is very interesting. For example, Here we encounter this space as a space of all possible modular invariant toroidal compactification. But this is also related to the modular space of complex two-dimensional Calabi-Yau manifold, which we will discuss later, has also a similar structure. In general, ONM divided by ON times OM is called Grassmannian. Manifold. And well, this is an example of Grassmannian manifold. And this has a various interesting geometric property. One of the properties it has is that you can think of this as a space of n-dimensional subspace in n times m-dimensional space of this particular signature. Okay. But there are various different interpretations of this Grassmannian manifold. And another important feature of this Grassmannian manifold is that it's related to free fermions. So you can represent geometry of Grassmannian manifold in terms of free fermions. So actually, in your class in quantum field theory, you might have heard that when you try to express a functional integral for fermion field, we need to use Grassmannian variable. And it's the same Grassmannian. And the reason that anti-commuting variables are called Grassmannian is it's actually because of this. That this space is called Grassmannian, and in order to describe the Grassmannian space, it's convenient to use the variables which anti-commute with each other. And so that's why it's, the anti-commuting variables are called Grassmannian. So that's sort of origin of the word. So one of the features of this particular space is that its dimension. So you can say that this is a moduli space. Moduli space of string compactification of this type, and this was considered by Narayan, so this is called Narayan moduli space. So the dimension of the Narayan moduli space, this moduli space, is d squared. So in general, actually, if you have a Grassmannian manifold of this type, then its dimension is n times m. Okay, you can easily count the dimension because the dimension of On is equal to 1/2 of n minus 1. And so therefore, and then dimension of this is the same as the dimension of O n plus m. So therefore, the total dimension is 1/2 of n plus m minus 1 minus 1/2 of n minus 1 minus 1/2 of m minus 1. So if I did the counting correctly, this is n times n, right? And so the dimension of this space is n times n. In that, just the number of dimension minus the redundancy gives you n times n. So in particular, the dimension of this Narayan moduli space is d squared. Okay, so this suggests that the construction that I started out was not generic. So I started out with this Lagrangian of string, like that, with this metric where xi goes to xi plus 2 pi integer. We started out with this Lagrangian, and then wrote Bij to be summation A of EIA, EJA, and introduced the lattice to be generated by EIA and its dual lattice. Right? So this was how we parameterized this thing. And we wrote that that's P left, P right of A to be equal, so this is P hat, to be equal to E star I N I plus G hat J M J, and this is lambda. So this is how we parameterize things, but we can easily see that this is not enough to cover the entire Narayan modular space, because Gij is a D by D symmetric matrix. So therefore the independent number of independent component is D, 1/2 of D and D plus 1. So this is for higher dimension, this is strictly less than D squared. So dimension greater than 1 actually, this is strictly less than D squared. So therefore you can see that the Narayan moduli space is not just a space of this compact, this method. So what is this that we are missing? Well, there is another possible way to deform this Walsh theory that we have ignored so far, which is to turn on the unsymmetric tensor field. So if you remember, if you consider the massless spectrum in bosonic string, you have metric, you have graviton, and you have unsymmetric tensor field, and then you have dilaton. So you have 3 types of degrees of freedom. So this Gij over here corresponds to the deformation by condensation of graviton. But we did not take into account this unsymmetric tensor field. In this discussion, dilaton does not play a role because change of the vacuum expectation value of the dilaton changes the string coupling constant. And so far we are only looking at the genus 1 amplitude, so fixed genus. So dilaton, change of the dilaton background does not change the description here. But we should consider taking into account unsymmetric form. So if you do that, then the action changes. So we need to consider including it. So if you include it, the action we should consider is Gij plus Bij of del of xi del bar of xj. Okay, so this is symmetric in I and j. This is unsymmetric in I and j. And so in total, the number of degrees of freedom of Bij is 1/2 of d plus 1. And number of degrees of freedom of Bij is 1/2 of d minus 1. And so if you sum them, you get d squared. And this is exactly what we need. Okay? So how does this change? So this is the particular lattice structure, but how does this change this lattice? Well, so if you do that, then what changes is the following. That so if you introduce this thing, then what happens? Well, if you write del is equal to, so remember that z is equal to sigma 0 plus sigma 1, and z bar is equal to sigma 0 minus sigma 1. So this contains derivative with respect to sigma 0 and sigma 1. So if you write out this term, this contains Gij of del 0 xi del 0 xj plus del 1 xi del 1 xj plus Bij del 0 xi del 1 xj, and there is a factor of 2. And it's because this is symmetric and this is unsymmetric. So 0, 0 term and 1, 1 term cancelled by the unsymmetry of I and j. So you get off-diagonal term. So in particular, if you think of sigma 0 as a worldsheet time coordinate, this means that the momentum variable conjugate to x is given by the derivative of the functional derivative of the action with respect to xi. So that means that the metric, in addition to the time derivative of xi coordinate, we get, well, we have 2 pi, I think. In addition to this, we get Bij of del 1 xj. So the moment, so before you turn on the unsymmetric field, the momentum conjugate to x is just the derivative with respect to x of x with respect to x0. But if you turn on B field, then it actually gives rise to derivative with respect to space coordinate. Namely, the relation between time derivative and momentum gets slightly shifted. This is actually very similar to what happens to electron in magnetic field. That well, you might have learned in electrodynamics that if you turn on magnetic field for electron, then actually the relation between momentum and winding changes. And it gives rise to all sorts of interesting things like Landau level under magnetic field. That if you turn on magnetic field on the plane, the electrons start rotating because of this force induced by magnetic field. And it gives rise to Landau level. And you can interpret it as caused due to the mixing of time derivative and space derivative in the definition of the momentum. And because of that, the momentum variable gets shifted, and that leads to the change of the lattice structure. Okay, so now actually the lattice is defined, is generated by 2 types of lattice point. Where EI hat is now equal to EIA plus BIJ EAJ star and then EI star is equal to star AI star A. So there is actually a change in the definition of lattice point. And you can actually prove, so this was actually proven by Narayan and Witten. So there is a nice paper by Narayan and Witten, where they show that this covers the entire Narayan modular space. So this covers OD divided by OD times OD divided by ODD over Z. Okay, so in this case, therefore, this Narayan moduli space turned out to have this nice geometric interpretation. So historically, what happened was that when Narayan first wrote this paper, he just assumed that modular invariance is the basic principle and tried to find the most general way to write one-loop partition function, and found that for whenever you have this even self-zero lattice, you can write down partition function. So this was a very interesting idea that you actually consider some abstract conformal theory and define the string propagating. But later, in this particular case, it was realized that it actually have a geometric interpretation in terms of this particular compactification. Okay, but this leads to a very interesting change of the perspective on string compactification. That you can actually consider some abstract conformal field theory and use it as a sort of target space of string theory. And in fact, you can build consistent string compactification. So this significantly broadened the scope of what's possible for the construction of string theory. So that was a very important insight. Okay, so that was sort of the introduction to some idea of how to use a modular invariance to put constraint on string compactification. So now we spent enough time on bosonic strings, so let's try to have more sort of realistic situations. So there are various unpleasant features of a bosonic string, and the most significant was the existence of tachyon. So this suggests that even perturbatively, this theory is actually unstable, and so we cannot even consider quantization of this string. So we need to find a theory which is absent and at least perturbatively stable. And another feature that was not desirable was that bosonic string contains no fermions. And so we'd like to have a theory which contains fermions. So that was that's another thing. So superstring was a way to sort of address both of these problems simultaneously. And as a bonus, it gives rise to a new type of space-time symmetry called supersymmetry. So I'd like to start discussing this. Okay, so superstring theory. Okay. So let's first start a review what we do in ordinary point particle, and then that's going to become introduction to string worship theory. So before we go to string, we start with point particle. So the Lagrangian, so if you have a point particle and when it is propagating along some trajectory, the trajectory is described by map from some tau in some line segment. I chose it to be arbitrary as between 0 and 1 to some point in target space. So if the target space is d-dimensional, then it's a point in d-dimension. So its trajectory can be parameterized like that. And if it is Minkowski space, for example, then the Lagrangian is described by the mass times 1 minus x dot square, where x dot mu square is, so this is equal to x0 square minus xi square. I'm using almost positive notation, so therefore minus x dot square is equal to minus d x naught d tau square plus summation I is equal to 1 t minus 1 dx I dt square. Okay, and then I put minus sign so that the time square term is positive. Okay, so that's sort of Lagrangian. And if you quantize this, you get the constraint, and the constraint becomes Klein-Gordon equation. I think we have reviewed this before, and but there is an equivalent description, which is to introduce yes, to introduce worldsheet metric, the world line metric. So we can also consider this Lagrangian, where E can be thought of as a metric in one dimensional space of this world line coding. Okay, so therefore, well, actually, the E square is a metric. E square is so you can think of this as a cosmological constant term, and this is a kinetic term. So this is sort of point particular analog of Polyakov action, whereas this is a point particular analog of Nambu-Goto type action. Okay, so remember that in bosonic string, we had the Lagrangian density, which goes like G mu nu square root of G mu nu del mu xi del mu xj, and this is the worldsheet metric. And if you eliminate this by equation of motion, you obtain the square root of determinant of del x. So this is a Nambu-Goto action, and then this is a Polyakov action. And then so you can relate this by integrating out the metric. Similarly, so you can think of this as analog of Nambu-Goto action. Okay. And what you can show is that just like in the case of string, because of the diffeomorphism invariance of the worldsheet, there are Virasoro constraints. So in this simpler model, there is also a constraint, and that gave rise to the Klein-Gordon equation. So that gave rise to the Klein-Gordon equation. Okay. So that was that I believe we discussed at the beginning of this course. So now let's supersymmetrize it. So so what we need to do to supersymmetrize. So we consider supersymmetric particle. So what we consider is again some map in d-dimensional space where x tau is mapped to x tau in d dimension. Okay, but this is a bosonic variable, and there are d of them. And then, in order to have supersymmetry on the worldsheet, for each bosonic variable, we need its superpartner. So I introduce some fermions, psi I, where I goes from 1 to D. Okay? And so we would like to generalize this term. So it turns out that generalizing this with this additional term is difficult. So let's just consider generalizing this. So we'd like to generalize this so that you can have also kinetic term for the fermions and supersymmetry is maintained. Okay? So the kinetic term for fermion, well, so that the kinetic term that we know about fermion is that for the Dirac equation. So you know that the Dirac equation is given by this form. So if you have massless Dirac field, it has this type of situation. Well, first of all, x from the two-dimensional perspective, one-dimensional perspective, x is a massless field. Because if you look at the equation of motion for x is something like this. So this is like D'Alembert is equal to 0 in one dimension. So x is in some sense massless scalar field in one dimension. So therefore it's natural that its partner is a massless equation. Now, but it's one dimension. So in one dimension, the Dirac matrix is identity. So therefore this is just del tau of psi is equal to 0. Okay, so you need a Lagrangian which gives you this equation. So it's natural to consider adding psi dot. Okay, that of course i's are contracted, so it's a psi dot. Now, if psi is a bosonic field, this will be total derivative because you could write psi dot as d tau of psi square divided by 2. But since psi is fermion, so psi square is equal to 0, so you cannot write it in this way. So this is actually not the total derivative, right? In fact, this is equal to minus of psi dot psi. So this is not the total derivative. Okay? So this could have been perfectly nice Lagrangian, except that of course we need to introduce metric to write the kinetic term. So this would be the natural Lagrangian. But it turns out that if you try to impose supersymmetry, this does not quite give you a nice local supersymmetry for the following reason. So E you can think of as a metric. So metric is also, I'm also making this metric as a dynamical field because we're going to integrate it to impose constraint. And we want the world line theory to be diffeomorphic invariant. So the metric should also be dynamical variable. So we are considering actually one-dimensional gravitational theory. And x is a bosonic variable of this gravitational theory, and psi is a fermionic variable of the theory. But metric is a bosonic variable. So metric also needs a superpartner to make the whole thing supersymmetric. So you have a metric, which is in general dimension, it's a symmetric D by D matrix. And its superpartner is called, so for example, in 2 dimension, it's a spin 2 particle. And we need an analog of that in 1 dimension. So namely that we need analog of graviton. So we need to introduce another additional term, and supersymmetry demands that it takes this form. So E is a metric or graviton, and nu is called Rarita-Schwinger field. These are people who introduced this field, and it's called gravity in 2 dimensions. And with that, we can have a closed supersymmetry transformation. On 1D world line, which is given by del x mu goes to I theta of psi mu, psi I, del psi I goes to theta of d tau of xi, and metric also transforms under supersymmetry, and the gravitino also transforms under supersymmetry. Okay, so this is supersymmetry transformation. So in the bosonic particle, we have diffeomorphism. And it gave rise to the constraint x dot square is equal to 0. And x dot, however, upon quantization is related to the momentum, which is equal to I del x. So it gave rise to the massless Klein-Gordon equation for the wave function. Okay, so in the case of bosonic string, a bosonic point particle, if you quantize the world line theory of bosonic particle, and if you impose diffeomorphism condition, and if you write it on the wave function on the quantized bosonic particle, it gives you massless Klein-Gordon equation. So this is something we discussed at the beginning of this course, I believe. So in superparticle, so we have super diffeomorphism. So that means that in addition to the constraint coming from diffeomorphism, we get a constraint where theta is a supersymmetric transformation parameter, can be arbitrary function of tau. So this gives rise to additional constraint, which is the x dot p, also x dot psi is equal to 0. Okay, so now if you quantize x dot is momentum, which is equal to minus I del xi, and psi satisfies anti-commutation relation. And the reason is that it's a kinetic term. So if I look at this kinetic term, then the momentum conjugate to x is equal to E times x dot I, right? And momentum conjugate to psi is equal to I times E times psi I. So if you, for example, take a gauge when E is equal to 1, then x dot is a momentum conjugate to x, and psi is momentum conjugate to psi. So therefore we have this commutation relation. Okay. So this means that x dot is actually a derivative operator, and psi is a Dirac matrix. There is actually a simple mathematical theorem. Well, it's just a simple theorem you can prove by linear algebra, that only non-trivial representation of this algebraic relation is given by Dirac matrix. This can be proven very simply. So whenever you see this, you see that it's a Dirac matrix, or its tensor product. So therefore, this condition imposed on the wave function means that the wave function satisfies Dirac equation, because x is derivative, psi is a Dirac matrix. So therefore, wave function satisfies the massless Dirac equation. Okay. So this is a very important insight. So that if you consider superparticle, then the constraint equation is a Dirac equation. Now, Dirac matrix D star has an important property that is, if you square it, it gives you the D'Alembert. In fact, this was a motivation of Dirac, right? Dirac wanted to take square root of the D'Alembert operator, and came up with this one. Well, so we can easily see that how this works. So this slash is equal to gamma I del I, and so therefore if you square it, you get del I, gamma J, del J. So, but this means that it's 1/2 of anti-commutator of gammas, and del I, del J. So if gamma is the same as psi, and if psi satisfies this condition, then you should get maybe there's a factor 2 here. Then we should get del I, the D'Alembert, right? But this is actually related to the supersymmetry. So Dirac must have realized that this is actually supersymmetry, because this means that the Dirac operator is a generator of supersymmetry in one dimension. But when you square it, it becomes the D'Alembertian, which is actually the generator of the diffeomorphism. These are generators of supersymmetry and diffeomorphism, and that's why we are setting it to be 0. That's a Gauss law constraint. Gauss law constraint imposes a condition that generator of gauge transformation vanishes. So these are the Gauss law constraint. For super diffeomorphism. And so this supersymmetry generator, Gauss law for supersymmetry generator is a Dirac equation, which squared to be the supersymmetry generator of diffeomorphism. So that's consistent. Okay, so that's superparticle. So this suggests that in one dimension, if you supersymmetrize the dynamics of point particle, bosonic particle, then whereas the bosonic particle gives rise to particle obeying the massless Klein-Gordon equation, if you supersymmetrize it, your wave function now satisfies massless Dirac equation. So this suggests that in order to remedy the problem of bosonic string that you don't have fermions, you can just supersymmetrize Walsh itself. And that should give rise to a sector of the Hilbert space which contains the fermion. Okay? Now, so this was not anticipated, but if you do that, you get two bonuses. One is that if you supersymmetrize Walsh theory, then it turns out that you acquire actually also supersymmetry in the target space. If you consider the theory in particular space-time dimensions. And so that's one important fact. And another important fact is that when you have supersymmetry, you automatically remove tachyon, because tachyon is not in the unitary representation of supersymmetry, so that is not allowed in supersymmetric theory. And in fact, if you have supersymmetry unbroken, then you can show that the Hamiltonian is automatically bounded below, so the theory should be stable. So it shouldn't have tachyon in it. And so therefore, by supersymmetrizing Walsh's theory, you can improve some of the problem we had in bosonic string in this way. Okay, so that's what we'll see in the next lecture. Yeah.
Would this one be n equals 1 or n equal a half supersymmetry?
On the worksheet,
For the particle, the superparticle.
yeah, but on the word line, you should count this as n equal 1 half, I think. In fact, in two-dimensional worksheet theory, I think that, yeah, so the counting of n is so complicated because it's dimension dependent. Typically, when you count supersymmetry, we count supersymmetry with respect to the smallest supersymmetry we can count. So this is the smallest supersymmetry, so you can say n equal 1. I think the better way to count is number of supersymmetry generated. So in this case, the number of supersymmetry generated is 1. So you can say it's n equal 1 in that sense.
So one supercharge?
One supercharge.
Okay.
One supercharge. Okay? Yeah, so by the way, at the beginning of this class today, I asked you the following thing. So I wanted to ask you, in lieu of homework, to make some presentation at the end of the course. But I realized that there are still 14 students enrolled in the class, which I was expecting by this time the enrollment to be significantly lower than that. But if you have 14 students, even if each student gives you 10 minutes presentation, it takes two days, and 10 minutes may not be enough, and also coming up with 14 projects might be challenging. So I'd like to instead suggest a possibility that maybe 2 or 3 of you can get together to do one project. So then each of the group can get half an hour or so, and if you have 6 groups, we still can do it in 2 classes, and then we can just have 5 or 6 projects, and that seems to be more manageable proposal. So I would like to ask you whether you are amenable to that. Do you think each of you have at least 2 or 3 friends? Okay, so let's do that. Well, thank you very much.